Welcome to this explainer. Today, we're going to completely rewire how you think about chaos, order, and honestly, the very thermodynamic reason you even exist to listen to me right now. We're taking a walk through one of the absolute strangest yet most beautiful ideas in all of science. We'll uncover exactly why a butterfly's wing beat became the most famous metaphor in modern physics, why a simple pile of sand can teach us about massive earthquakes, and why the universe seems to build these magnificent, complex structures precisely because of its relentless drive toward chaos, not in spite of it. Section 1. The paradox of order. So, let's start with a massive contradiction. If the universe is doomed to eventually slide into total thermodynamic disorder, how on earth do you exist at all? You see, the second law of thermodynamics dictates that entropy, which is basically a measure of disorder, has to relentlessly increase in any isolated system. Basically, over time, the universe really wants to drift towards statistical blandness, just a featureless soup. So it's this profound mystery why our universe is absolutely bursting with beautifully ordered structures. I mean, think about spinning galaxies, perfect six-sided snowflakes, or the incredibly complex human brain. If the fundamental rules say things fall apart, why are so many things coming together?
To solve this paradox, we've kind of got to separate casual randomness from what we call physics chaos. Casual randomness is like my famously messy desk, right? Absolutely no rules apply there. But deterministic chaos, that is not random at all. It's actually governed by strict, unbreakable mathematical laws that amplify tiny atom-sized differences exponentially. Imagine twins born just a second apart, starting their lives with positions that differ by the width of a single atom. In a truly chaotic system, that microscopic difference grows and grows until they end up in completely different worlds.
Section 2. Redefining chaos. For centuries, scientists believed that a deterministic universe meant we could have perfect predictability. Isaac Newton gave us this beautiful idea of a clockwork universe. The thought that if you just knew where every single particle was, you could predict the future forever. But that comforting vision started cracking in the late 1800s with Henri Poincaré's three-body problem, where he realized that tiny starting differences totally ruined long-term orbits. And then it just completely shattered in 1961, thanks to a computer glitch that changed science forever. That specific 1961 glitch actually gave us the legendary butterfly effect. Meteorologist Edward Lorenz was running a weather simulation, and he decided to round a variable from 0.506127 to just 0.506. He just chopped off a microscopic, seemingly meaningless fraction. But by doing that, he accidentally proved that an infinitesimally small disturbance, literally like a butterfly flapping its wings, could mathematically alter the long-term future of a massive system. It showed us the fundamental impossibility of tracing causal chains. You can have perfect laws in place, but because you can never, ever measure the present moment with infinite precision, predicting the distant future is just fundamentally impossible. And this extreme sensitivity brings us to the Feigenbaum constant. Take a look at this very specific number, 4.66920016. This was a completely jaw-dropping discovery from the 1970s. Mitchell Feigenbaum proved that the mathematical route from orderly, predictable behavior into pure chaos is governed by this exact universal number. It literally does not matter if you're looking at a dripping faucet, wildly fluctuating rabbit populations, or lasers. As they transition from stable repetition into wild chaos, the intervals of those cascading changes shrink by this exact universal ratio. It's like a hidden mathematical architecture that connects all chaotic systems across nature. Section 3. How chaos builds order. So how do we get order from all of this? Well, Nobel laureate Ilya Prigogine finally resolved our grand paradox. He proved that when a system meets four specific conditions, it has to be an open system, pushed far from equilibrium, governed by nonlinear dynamics, and it must continuously export entropy. The relentless dissipation of energy actually doesn't destroy order, it manufactures it. He called these highly organized, self-sustaining patterns dissipative structures. Prigogine actually coined a really beautiful phrase for this mechanism: order through fluctuations. Think of it this way: rather than a universe just lazily sliding into a featureless soup, open systems actively feed on flowing energy. They seize upon tiny, totally random microscopic fluctuations, these little sparks of chance. And then the system's deterministic nonlinear dynamics steps in to sculpt and amplify those sparks into magnificent, robust, macroscopic structures. It's chance and necessity working perfectly together to build the world around us. Section 4. Patterns in nature.
The wild thing is, without any central conductor telling things what to do, raw thermodynamic dissipation spontaneously births stunning phenomena everywhere. We see it in Boehner convection cells, which form these perfect geometrical honeycombs in heated oil. We see it in Turing patterns, where diffusing chemicals unexpectedly destabilize to generate the spots on a leopard. And we see it in Kuramoto's synchronization. That's the mathematical framework governing the rhythmic lockstep flashing of millions of fireflies. And get this, even the electrical coordination of the pacemaker cells in your very own heart.
Which brings us to another mind-blowing phenomenon, self-organized criticality. Physicist Per Bach showed that countless natural systems automatically tune themselves to a delicate critical threshold. It's a lot like a physical sand pile that you keep dropping sand onto. It grows steeper and steeper until it's constantly on the absolute verge of collapsing. Whether you're looking at tectonic fault lines triggering massive earthquakes or the neurons firing away in your brain, they hover right at this edge. And they all share the exact same mathematical power law signature for avalanches. Small events are super common, massive ones are rare, but they all scale beautifully without any outside tuning whatsoever.
You can even look up at the sky to see this. The breathtaking aerial ballet of hundreds of thousands of starlings emerges entirely from individual birds following just 3 incredibly simple local rules: separation, alignment, and cohesion. By simply paying attention to their immediate neighbors with zero centralized master plan and no leader bird calling the shots, they generate a hyper-coordinated, swirling mass. It ends up behaving almost like a single living organism, poised right at the edge of a phase transition, allowing it to instantly dodge predators.
Section 5. The physics of life. Let's bring this all back to you. In 1943, quantum physicist Erwin Schrödinger recognized that life actually doesn't violate the laws of physics. Instead, a living organism survives by, as he famously put it, constantly consuming negative entropy from its environment. You aren't somehow defying the universe's drive toward disorder, you are surviving by directly feeding on its existing order. You, my friends, are the ultimate dissipative structure. You actively maintain your internal biological perfection by taking in highly ordered, low-entropy food and sunlight. But you pay a really steep entropy tax for that privilege. You pay it with a massive, continuous dump of highly disordered waste and heat right back out into the cold universe. Just like a whirlpool in a draining bathtub, your form stays constant, but maintaining it requires a relentless, never-ending flow of energy. You create local order by actually funding the universe's overall slide into disorder.
Now, this isn't just historical theory. Cutting-edge research in 2026 is moving incredibly fast and continues to push these exact boundaries. Scientists are developing models of stochastic determinism, mathematically proving how random fluctuations act as the literal engine of structural order. After decades of trying, they've finally rigorously proven self-organized criticality in specific one-dimensional random walk models. And even better, they're bridging this abstract physics with highly practical biomechanical applications, doing things like mapping human locomotion and even predicting the outcomes of spinal surgeries. The frontier is rapidly expanding right as we speak.
All of this leaves us with a pretty profound question to wrap up on. If chaos and order are eternal dance partners, are you simply the universe's most magnificent chaos surfing machine? Ultimately, your heartbeat, your complex brain, your very existence, they are not fragile islands hopelessly fighting against a chaotic sea. They are actually the most brilliant achievements of chaos itself. You surf the flow of entropy every single day. Thank you so much for joining me on this explainer. I really hope this leaves you seeing the swirling patterns in your coffee cup and the beating of your own heart with just a little bit more wonder.